Okay, so today's lecture is on combined loading analysis, and we are going to relate combined loading stresses into principal stress, and I'll explain why. Okay, when we go further into the lecture, right? So the first thing we're going to start on is we're going to talk about analyze analyze structure under combined loading. So what do I mean by combined loading? Okay, so there'll be loading induced by bending moment. Okay, so we get bending moment and axial loading. So the formula to use is going to be stress, right? Is equal to P over A. So we know that this P over A, this is due to axial loading. Then plus, okay, by My over Iyy multiplied by Z. And then we can plus again by Mz over Izz multiplied by Y. So we're going to look at two moments now, okay? One moment, this moment over here is on the y-axis, acting about the y-axis. This moment over here is acting about the z-axis. Okay? And this is due to bending moment. Okay? So you still have to remember what you have learned before week 10, okay? Right? Because this is one chapter that integrates everything, whatever we have learned. This is like the grand finale, okay? And it also has most circle. That's why we have principal stress. Then we also, so if I were to sketch the distribution, okay, of the normal stress, so as usual, if this is our normal stress, and this is our y displacement, or a distance along the cross section of beam. Okay, so distance along cross section of structure. So this is the cross section distribution. What we see is over here, you'll see a distribution. This is just an example. Okay, we'll see a distribution doing this. Okay, where over here is compression, and then over the other side is in tension. And this position is so-called our neutral axis. Okay? So I want you to take away, excuse me, I want you to take note on how the normal stress has been distributed. Okay, so that is due to normal stresses. Okay, so we have bending moment and we have axial load. Then the next thing that we're going to have, okay, so the next
Sorry, Eugene, for the bending moments, we're not taking into account the thickness.
bending moment, we're not taking account into thickness. Yes, we are. It's the Z direction, right?
Yeah, but that's the distance from
The
the.
neutral axis, right?
Yeah,
So what do you mean by thickness? Thickness is taken account by BD cube over 12 already, right?
BDQ.
second moment of area.
Okay, so this is not the same as. Oh yeah. Because I'm confusing it with
Good
the.
morning.
I'm confusing it with the other one, with the one that uses shear. Yeah, my bad.
Okay. All right. We still have shear. Okay. Then we also have loading. Okay, loading under the loading under shear force. The shear force. Right. So remember shear force. So shear force is shear is equal to Vy over Izz, right? Multiplied by Qz divided by T, right? So I want you to recognize the formula is bending moment if it's My over Iyy multiplied by Z, okay? For shear is Vy over Izz multiplied by what? Qz, right? So that is the difference, okay? Crash out again, coming back again, okay? Right? So that is the difference that we see in terms of bending moment. Okay, in terms of bending moment.
I also have one question. Is that neutral axis the same as the centroid, or is it
No,
would it be
no, neutral axis is not always the same as centroid.
okay?
Centroid is geometrical, neutral axis is stress base. Okay. Now
Okay.
someone asked me that when you say long question, how long the same length as term test one? Yeah, the same length as term test one and term test two. Okay. Because someone asked me about the term test. Okay. Right. So coming back to where we were, so the shear stress is equal to By over Izz Qz divided by T, or if it's in the Z direction, this will be equal to Iyy Qy divided by T. Okay. So a very interesting thing, if we now look at the shear stress distribution. So what I'm going to do, I'm going to move this down. So you, right. A very interesting thing about this distribution now is this is my shear stress, right? Right there, hold on, that is my shear stress. And then I'm going to draw the position of my neutral axis. Sorry, my y-axis, right? So this is our shear stress. This is again the distance along the cross section, okay, of structure. So as you all can remember, in terms of the in terms of the distance, okay, what we have is at the location of the centroid or the neutral axis for this case, right? You have this sort of distribution, right? So this is our, oh, I did not draw arrow for you guys in the first place, I will not. So this is the sort of distribution, right? We've seen this before. The thing now is this, the tau max, right? The tau max is on this axis of the neutral axis position that I've drawn. Okay. Okay. Whereas the bending moment max, right? The bending moment max, you can see, is over here. So this is positive, and this is negative minimum, right? So when you design your structure, where will you use? Do you use the neutral axis where you have maximum shearing stress, or will you use the bending moment, okay, which is furthest away from the neutral axis, right? So which one to use, I will cover in this topic, okay, this topic. So this is where it's interesting now down here, okay? Where will you use, right? So another thing that I'm going to briefly talk about, okay, and this is not covered in our syllabus, but it is just one more set of formula to apply is torque. So for torque over here, we are going to focus on round or circle cross section. Okay, I did not cut. I'm not going to do rectangular, which you can. Okay, circle cross section. So torque in circle cross section, right, is equal to the shear stress is equal to TR over J, right? So this formula over here, it looks pretty new, right? But it's nothing complicated. Okay, I'll tell you why it's nothing complicated. Where T represents the torque, which is in Newton meter, okay, or pound inch. R is the maximum radius. Oh, you guys can't see now. Apologies. Oi, it's not you, it's me. Okay, the thing crap out again. Don't worry, I'll bring it back to you guys. R is the radius or maximum radius. And J is the polar moment of area, which is meter per 4. And the relationship J is equal to twice of the second moment of area. Okay. So for cylindrical, J is equal to pi over 2, right? R naught to power of 4. Okay, so this is for solid. And then for hollow, R naught is R outside, R I is R internal. This is for hollow. Okay, as I said, we are only going to focus on the circular cross section. Okay, so if I were to now construct how the shear stress distribute, right, it's not the same as the one induced by the shear force now. Okay, it's going to be the same as the one used for bending moment. The trend will be the same now. Okay, so this is the distance again. So what you'll see again, you are for this case, there's no positive or no negative. Okay, so I'm going to use everything. Wait, is there positive? There will be direction, which I'll teach you how to analyze later if there's time. If not, I will not test you on it. So this is how your shear stress will be distributed. Okay, so this is how your shear. So again, for this case, your shear max is at these two location. Okay. Okay, your shear max. So these 2 points, I should have done this earlier. My bad. I will redraw. Right, so if I draw a line down, they should be at the same point. Okay, now it happened not to be, my bad.